Welcome, curious minds, to another deep dive brought to you by Knowledge Flow. Have you ever paused to consider the silent symphony happening behind the scenes of your digital life?
Yeah.
Every tap on your phone, every search you make, every single video you stream all relies on this intricate, invisible dance of information. How do our devices and our digital experiences handle the sheer, mind-boggling volume of data we interact with every single day? Today, we're taking a deep dive into the foundational concepts that make it all possible, data structures and algorithms.
That's exactly right. Our mission today is, to give you a shortcut, to understanding these core techniques. Think of them as the hidden blueprints for storing and manipulating data with incredible efficiency. We're going to pull back the curtain, reveal the elegant solutions to sometimes incredibly complex problems, and maybe uncover some surprising facts about how digital systems truly work. It's really a journey into the very architecture of the digital world.
And the beauty of this deep dive is that it's directly relevant to you. I mean, regardless of your technical background, these concepts aren't just for, software engineers or computer scientists. They're the invisible scaffolding that supports everything you touch digitally. From how quickly your search results pop up, to how smoothly your favorite streaming service delivers content, or even how social media feeds seem to, magically organize themselves. Understanding them truly provides an incredible aha moment about the technology that surrounds us. So, are you ready to explore the hidden logic? Let's jump right in.
Okay, so when we talk about the architecture of the digital world, it all starts with organizing information. So at its core, what exactly is a data structure? It sounds a bit academic maybe, but I imagine it's quite practical.
Oh, it's incredibly practical. Imagine you have a library. A data structure is essentially the librarian's system for organizing all the books, how they're categorized, shelved, and indexed. It's a technique, or really a study, of how to store a bunch of data in an organized manner so that it can be used very sophisticatedly, very efficiently when you're designing programs and algorithms. In simpler terms, it's about storing data and then being able to fetch it from any part of the computer's memory in an organized way, precisely when it's needed. It's truly a vital subject in information and computer technology.
That makes perfect sense, like the Dewey Decimal System for data. And it feels like such a fundamental concept. It must have been around for a while, right?
Yeah.
Do we know when this term data structure really came into its own?
That's interesting. It's actually a relatively modern term in the grand scheme of computing history. The term data structure was first coined, formally anyway, back in 1976. It was by a highly influential computer scientist named Nicholas Wirth in his groundbreaking book, Algorithms plus Data Structures equals Programs. That book laid down many of the fundamental details of computer programming that, we still adhere to today. So while the ideas existed, he really formalized the term.
Right, Wirth. Okay. So if a data structure defines how data is stored, then what about something called an abstract data type, or ADT? It sounds like another layer of abstraction. Is it like a blueprint for the librarian system, maybe, without specifying the exact shelves or the type of wood they're made of?
That's a fantastic analogy, yes. Abstract data types, ADTs, are exactly that. They define the logical behavior of data structures without actually specifying how they are implemented under the hood. Think of them as a high-level interface, like a contract. They focus entirely on what operations can be performed on the data, like add an item or find an item, rather than how those operations are carried out internally, whether it's through a complex system of pointers or just simple memory blocks.
Okay, so it's like saying I need a list where I can add and remove items, and I don't really care at this stage if that list is built using a simple fixed size array, or maybe something more fluid like a chain of interconnected elements.
Precisely. Exactly. Common ADTs include conceptual ideas you might already recognize, maybe even intuitively. Things like a list, a stack, a queue, a deck, a set, a map, and a graph. Each of these ADTs defines a specific set of operations like insertion, deletion, searching, and traversal. The real genius here is that while the operations are defined by the ADT, they can have multiple underlying implementations. For instance, like you said, a list ADT could be implemented as an array, or it could be implemented as a linked list. Each has its own strengths and weaknesses, but both still adhere to the fundamental list behavior defined by the ADT. This approach is incredibly valuable for modular programming. It makes code more reusable, easier to understand, and much simpler to maintain in the long run.
Okay, so we've got this foundational understanding of what data structures are. But here's where it gets really interesting for you, our listeners. Why should you care about these seemingly abstract concepts? Are these just academic ideas, or do they truly impact the technology you use every single day?
Oh, they absolutely do. These concepts are the bedrock, the absolute foundation of efficient computing, and they have a direct, tangible impact on your digital experience. There are probably 5 key reasons why they're so important. First, they enable efficient data management. I mean, imagine trying to find a single email in an inbox with billions of messages if they weren't organized somehow. Without well-defined structures, processing vast amounts of data would be chaotic and incredibly slow, maybe impossible.
Right, it would be unusable.
Exactly. Second, they contribute directly to optimized performance. This is huge. By choosing the right data structure for the job, you can dramatically reduce both the time it takes for an operation to complete, like a search, and the amount of memory it consumes. Think of it this way. If Google search used, say, a simple linear search, checking one web page after another, sequentially, you'd be waiting hours, maybe days, for a single result. But because they use incredibly optimized data structures and algorithms, your search results prop up almost instantly. That's the difference data structures make.
That's a powerful example.
It really is. Third, they are crucial for scalability. In today's world, systems aren't just handling a few thousand pieces of data, they're handling billions, even trillions. Data structures allow systems to grow and expand to these massive scales without performance just falling off a cliff. Fourth, they promote code reusability. By using established data structures, developers can build modular programs. This makes their code more maintainable and adaptable across different applications, saving immense development time and effort. And finally, crucially, they form the algorithm foundation. They support efficient problem solving. They make it possible to tackle complex computational tasks, things like mapping the entire internet, or optimizing global supply chains tasks that would otherwise be simply unmanageable. They are truly the hidden engine that makes the digital world turn.
It makes perfect sense. A hidden engine. I like that. So regardless of the specific structure we're talking about, whether it's organizing your photos or tracking stock prices, are there common fundamental operations that apply across the board? A sort of universal toolbox maybe for interacting with data?
Precisely. A toolbox is a great way to put it. There are a few general operations you'll find common to almost all data structures. These are like the basic verbs of data manipulation. First, traversing. This means systematically accessing or visiting each record in the structure, usually to process it in some way, like reading every item on a grocery list, one by one. Then, searching. This operation is about finding a specific record, or maybe just its location based on some key value, like finding a specific book by its title in that organized library we talked about. Insertion. This is simply adding a new record to the structure, like adding a new contact to your phone. Pretty straightforward. Deletion. The opposite of insertion, it's about removing an existing record, like deleting an old email. Sorting. This involves arranging records in a specific needed order, like arranging numbers from smallest to largest, or names alphabetically. Think of organizing your music playlist by artist or title. And finally, merging. This is the process of combining 2 sets of records, or perhaps more commonly, 2 already sorted lists, into a single cohesive file or list. Imagine combining 2 separate guest lists for an event into one master list, keeping it sorted. These 6 operations really form the fundamental actions performed on data within almost any organized structure.
Okay, great foundational overview. With that understanding, let's dive into the specifics, starting with what we call linear structures. These are some of the most fundamental ways data is organized. And first up are arrays and strings, really, the absolute building blocks of organized data. So what's an array, fundamentally?
Right, arrays. An array is perhaps the simplest data structure that exhibits linearity. Imagine a row of mailboxes, right? Each one has a unique number painted on it. An array stores elements, but crucially, elements of the same type, like all numbers or all names in adjacent memory locations. They sit right next to each other in the computer's memory, just like those mailboxes lined up in order. Its primary strength, its superpower really, lies in its fast access. You can directly and very quickly retrieve any element just by knowing its index, its position number, like knowing the number of the mailbox you want to check. Zap, you're there.
And how do we even refer to these elements, these mailboxes, in an array? Are there different ways to note them down?
Yes, there are a few common notations you'll see. If you have an array named, say, K with elements, you might see them referenced by subscript notation, like X zeros, and so on, like in math. Parenthesis notation, maybe K1, K2, K3. Or, and this is very common in programming languages, bracket notation, K1, K2, K3. In that bracket notation, like KY, Y is called the subscript or index, and KY as a whole is a subscripted variable representing the element at that position. A key point about arrays, though, a limitation really, is that they typically have a fixed size once they're created. You can't easily add more mailboxes to the middle of the row once it's built without a lot of, shuffling.
Right, the fixed size seems like a big constraint. So what kinds of things can you actually do with arrays beyond just putting data into those fixed slots? What are the standard operations?
Yeah. Beyond just storing and accessing, arrays support several important operations. First, traversing. We mention this generally, but for arrays, it means iterating through the array element by element from start to finish to carry out some process. For instance, if you wanted to count how many A grades were in a list of student scores stored in an array, you would traverse it. Conceptually, it's straightforward. Step 1. Repeat for BL to U, applying process to AB. Step 2. Exit. Basically, loop from the lower bound L to the upper bound U and do something to each element AB. Then there's inserting and deleting. Now, inserting or deleting an element at the very end of an array, if there's space, is relatively straightforward. But it becomes much more complex, much more costly when you need to do it in the middle. This is because of the array's linear, contiguous property. Everything has to stay packed together. If you insert an element in the middle, you have to physically shift all subsequent elements one position down the line to make space.
Oof, yeah.
Exactly. Imagine adding that new mailbox in the middle of our row. You'd have to physically pick up and move every single mailbox after it down one spot. Similarly, if you delete an element from the middle, you have to shift all subsequent elements back to fill the gap so there are no empty slots in the middle. For deletion, the conceptual algorithm looks something like: Step 1, get the item you're removing, say item AK. Step 2, then repeat for J at MCO M1, where M is current size. Step 3, shift everything back. Set AJ plus 1. Step 4, decrease the size counter. Set ending and none 1. Step 5, exit. It's a very costly operation in terms of time for arrays, especially large ones.
Okay, so insertions and deletions in the middle are tricky. But arrays are also used in more complex mathematical operations, right? Like matrix multiplication. How does that work conceptually with arrays?
Absolutely. Arrays, especially 2D arrays, are fundamental to representing matrices, which are basically grids or tables of numbers like spreadsheets. To multiply two matrices, say matrix A and matrix B, and store the result in a new matrix C, we typically use a set of nested loops. It's like for each cell in the resulting matrix C, say at row I and column J, CJ, you're performing a series of multiplications and additions. You take elements from row I of matrix A and multiply them by corresponding elements from column J of matrix B, and then sum up those products. The algorithm looks roughly like this. Step 1, repeat step 2 to 4 for I as you'll 1 to N, rows of A. Step 2, repeat step 3 to 4 for J still 1 to M, columns of B. Step 3, initialize the result cell, set Cij will 0. Step 4, repeat for K, columns of A, rows of B. Step 5, perform the core calculation, set Cij plus AIK BKJ. Step 6, exit. It's a very common array operation in scientific computing, graphics, machine learning, you name it.
Got it. Nested loops doing the heavy lifting. After operations like insertion and deletion, or even just initially, getting data into some kind of order is often crucial. That brings us to sorting. What does that involve fundamentally? And maybe give us a quick taste of how one method, like bubble sort, works, even if it's not the best one.
Right. Sorting is all about rearranging elements in a specific manner, usually in increasing or decreasing order. For example, if you have the numbers 8, 4, 5, 7, and 1 in an array, after sorting them in increasing order, you get 1, 4, 5, 7, and 8. It's essential for making data more manageable and critically much faster to search later on. Now, a very basic, intuitive sorting technique is called bubble sort. It's often the first one people learn. Imagine you have those numbers, 8, 4, 5, 7, 1, maybe represented as bubbles in a glass. Bubble sort works by repeatedly stepping through the list, comparing adjacent elements, PM1 with PM for instance, and swapping them if they are in the wrong order, like if PM1 should be less than PM but isn't. With each pass through the list, the largest unsorted element bubbles up to its correct position at the end. Then you repeat the pass on the remaining unsorted portion, which is now one element smaller, and so on, until the entire list is sorted. It's simple to understand, conceptually clear, but, and this is a big but, it's famously inefficient for large data sets.
Yeah, I've heard that.
It's what we call an ON algorithm, meaning if your list doubles in size, the time it takes to sort might quadruple, roughly speaking. So you'll almost never see it used in real-world high-performance applications. It's fantastic for learning the concept of sorting and swapping, but a performance nightmare in practice.
That's a fantastic distinction. Great for teaching, not for production.
Okay.
So once data is sorted, maybe using a better algorithm, finding specific information becomes a lot easier. That brings us to searching. What are the main ways we search through arrays?
There are two primary search methods for arrays, kind of mirroring the sorted-unsorted idea. First, linear search. This is the simplest but often the least efficient, especially for large arrays. You start at one end of the array, say the beginning, and you go all the way to the other end, checking each element one by one sequentially until you find the data you're looking for. Or you reach the end of the array and realize it's not there. It's like looking for a specific book on a completely disorganized shelf by examining every single book from left to right. It works, sure, but it can be very slow. Its time complexity is O(n) proportional to the size of the array.
Okay, the brute force method. What's the alternative?
The alternative and much more efficient method is binary search. But, and this is the crucial prerequisite we mentioned, the data must be sorted beforehand for binary search to work. Imagine trying to find a word in a physical dictionary. You wouldn't start reading from page 1, right?
No, you'd open it somewhere in the middle.
Exactly. You'd open it roughly in the middle. Then you check, is your word before or after this page? You've immediately eliminated half the dictionary. You then take that relevant half and you divide it in half again, check again, and so on. You repeatedly have the search space until you pinpoint your value or determine it's not there.
Yeah.
This is incredibly fast for large sorted data sets. Its time complexity is O log n, logarithmic. That means it scales remarkably well. If your data set goes from 1,000 items to 1,000,000, the number of steps needed for a search only increases by a small fixed amount, not proportionally like linear search. It's a huge win for sorted data.
Logarithmic, that's the key. Okay, we've mostly talked about linear arrays, like a single row of mailboxes, but what happens when you need to represent data that's more complex, like a table or a grid? That's where multidimensional arrays come in, right?
That's correct. Multidimensional arrays are simply arrays that have more than one dimension, which means they use more than one subscript or index to reference their elements. The most common type is a 2D array, which perfectly represents a matrix or tabular data. Think of a spreadsheet with rows and columns. You access an element using two indices, like matrix, row, column. You can also have 3D arrays, like a cube of data, or even higher dimensional arrays for representing more complex data relationships. They certainly enable efficient organization for these kinds of grid-like structures. However, they also require careful memory management because they can consume a lot more memory, and navigating them gets more complex. To illustrate quickly with code, imagine a 2D array in C in matrix 23 equals 1, 2, 3, 4, 5, 6. You could access the 2 point with matrix 01, and to print the whole thing, you'd use nested loops, one for rows I, one for columns J, printing matrix I inside the inner loop.
Gotcha. Nested loops again for navigating the dimensions. And related to arrays, there's this concept of pointer arrays. How do those fit in, and what do they allow us to do differently?
Right. Pointer arrays introduce a layer of indirection, which can be very powerful. Instead of storing the actual data elements directly within the array slots, a pointer array stores memory addresses, essentially. Pointers that point to other locations in memory where the actual data resides. Think of our mailboxes again. Instead of containing the letters themselves, each mailbox contains a note telling you where in the post office building to find a specific pile of letters. If X is a pointer variable pointing to an element in some data called value, and another variable B holds the memory address of an element in value, then B is called a pointer. An array of these B's is a pointer array. This allows for modifications to structures in a very space-efficient way, especially when dealing with data items of varying sizes like strings, or data that isn't neatly stored in one contiguous block. It gives programmers a lot of flexibility in managing memory and linking disparate pieces of data together without having to copy large blocks of data around.
Okay, that makes sense. Moving on from pure numbers or structured data, a huge amount of the data we interact with daily is text. That brings us to strings. What exactly are strings in the context of data structures beyond just, the words we type?
Fundamentally, strings are simply character data arranged in a sequence. That's the core idea. These characters can include the standard alphabets, both uppercase, AZ, and lowercase, digits from 0 to 9, and a whole variety of special characters you see every day on your keyboard. Plus signs, hyphens, slashes, asterisks, parentheses, commas, periods, dollar signs, equal signs, quotes, and so on. They are the fundamental way we represent words, sentences, code, web addresses, any kind of text within a computer system.
So how are these sequences of characters actually stored in the computer's memory? Is it always the same way, or are there different approaches for efficiency or flexibility?
That's a great question. There are actually 3 main types of structures or strategies for storing strings, and each comes with its own set of trade-offs. First, you have fixed length structures. In this method, each string is allocated the exact same predetermined amount of memory space, regardless of how short or long the actual string is. The main advantage here is incredibly easy access and update, because you always know precisely where each string starts and ends in memory based on its index and the fixed length. However, the major downside is potentially significant memory waste. If you allocate space for 100 characters, but most of your strings are only 10 characters long, you're wasting 90 characters worth of space for each one, often filled with blank spaces or null characters. And theoretically, changing even one character might mean manipulating the entire fixed-length block, which isn't ideal.
Right, that sounds potentially very wasteful. What's the next option?
The second approach is variable length structures, but with a maximum limit set. This is generally more efficient in terms of space. Storage here can be done in a couple of common ways. One way is by using a specific marker character, often called a sentinel or terminator, to signal the end of the string. The most famous example is the null character, used in the C programming language. The string occupies only as much space as it needs, plus 1 byte for the terminator. Another way is to store the length of the string explicitly as an integer value, usually right before the string data itself, or perhaps in a separate pointer array alongside a pointer to the string's start. This also avoids the excessive blank space of fixed-length structures, but you do have that maximum limit to consider.
Okay, variable length seems more practical. And the third type?
The third way is using linked structures. This is quite different. In this approach, memory cells are assigned to individual characters, or sometimes small groups of characters. Critically, each cell or node also contains a link or pointer that provides the memory address of the cell containing the next character, or chunk, in the string. This creates a chain of characters, much like the linked list we'll discuss more later. This allows for very flexible storage that doesn't waste space like fixed-length structures, and doesn't necessarily have a hard maximum limit like the second type. It's ideal for situations where string lengths are highly unpredictable or can change dramatically.
Very interesting. Different ways to chain characters together. Beyond just storing them, what are the common operations you typically perform on strings? Things we might even do subconsciously in a word processor?
Yeah, there are several key string operations that are fundamental. Substring extraction is a big one. This is about accessing just a part of a larger string. Think of extracting a first name from a full name string. To do this, you typically need 3 key pieces of information: the name of the original string, the starting position index of the substring you want, and the desired length of that substring. Indexing, or finding the position of a pattern, is another. This is often performed using pattern matching algorithms, which we'll touch on. It tells you where a smaller string occurs within a larger one. Concatenation is simply the act of joining 2 or more strings together end to end to form a new, longer string, like combining hello and world to get hello world. It's often denoted by operators like plus or sometimes fess. So PB would mean the characters of string P immediately followed by the characters of string B. And of course, finding the length of a string, just counting the total number of characters it contains. Beyond these basic manipulations, there are also general word processing type operations, which are essentially ways to modify string data more substantially. These often include replace. This involves finding occurrences of a given string, a pattern, within a text and replacing them with another string. Think replace, text, old pattern, new pattern. Insertion. This is used to add or insert a new string into an existing text at a specific location, like insert, text location string toad, and deletion. This is for removing a portion of a string, often specified by its starting position and length. For example, delete, string A, index A, B, length B, could mean deleting the first occurrence of string B from string A. These are the fundamental building blocks for text editors and word processors.
All right. Replace, insert, delete, the basics of editing. You mentioned pattern matching again. This sounds like a really core task, especially when dealing with large amounts of text data like searching web pages and DNA sequences. What are the general approaches to finding if a specific string pattern appears within another larger string?
Pattern matching is indeed a fundamental task in computer science. You're essentially trying to answer the question, does this smaller string pattern, let's call it pattern A, appear anywhere within this larger string, text D? When discussing the algorithms formally, you often see characters denoted by lowercase letters like X, Y, Z, and sometimes exponents are used as shorthand to denote repetition. For example, XY-oxy would represent the string A-psi-psi, or PQ would mean PQ, PQ, PQ. And just as a note, the empty string, a string with no characters, is commonly denoted by the Greek letter lambda. Now, there are a couple of classic algorithms for this, representing different levels of sophistication. The first pattern matching algorithm, often called the naive or brute force method, works very simply, just as you might intuitively try it. It compares the pattern A with each possible substring of the text D that has the same length as the pattern. It starts at the beginning of the text, compares the pattern. If it doesn't match, it slides the pattern over by one character in the text and compares again. It keeps doing this, moving from left to right, one character at a time, until either a complete match is found or it has checked all possible starting positions in the text. The algorithm might look like this. Step 1, set B, start index in text. 1, max text length, pattern length plus 1. Step 2, repeat step 3 to 5 while B equals max. Step 3, repeat for Q1 to pattern length. If pattern Q, text B plus Q1, then go to step 5, mismatch. Step 4, match found. Set index equals B and exit. Success. Step 5, no match at this position, slide pattern. Set B equals B plus 1. End of step 2, outer loop. Step 6. If loop finished without success, set index equals 0. Step 7, exit. The important thing to note here is that the time complexity, the time it takes for this naive algorithm, is typically quadratic, in the worst case roughly O and M, where N is the text length and M is the pattern length, often simplified to O and the similar lengths. This means for very long strings can get incredibly slow. If your text or pattern size doubles, the time might quadruple.
Oof, N squared again. That sounds bad for, say, searching the entire web. So if that's the naive approach, there must be a more efficient way to search for patterns, right?
Exactly. The naive approach is simple but slow. The second pattern matching algorithm represents a class of much more efficient algorithms. These algorithms use a clever trick. They pre-process the pattern A itself before they even start looking at the text D. They build some kind of auxiliary data structure like a table or state machine based on the pattern. This pre-computed information helps the algorithm to skip large portions of the text that couldn't possibly lead to a match based on characters seen so far. Famous examples include the Knuth-Morris-Pratt (KMP) algorithm and the Boyer-Moore algorithm. The conceptual algorithm might involve steps like Step 1, pre-compute the table state machine from pattern A. Step 2, set B, index in text, W1, Y, current state, initial state. Step 3, repeat steps 4 to 5 while current state, final match state, and B text lengths. Step 4, read next character HK from text B. Step 5, update state, E next transition function, current state HK. Step 6, increment text index, set B plus 1. This is highly abstract. The key takeaway is that the time complexity for these smarter algorithms is typically linear, roughly ON plus M, often simplified to ON because the text is usually much longer than the pattern. This is a monumental improvement over the naive algorithm's ON complexity. It's much, much faster, especially for long strings. If your text or pattern doubles in size, the time it takes roughly just doubles, rather than quadrupling or worse. This is why they are used in practice in text editors, search engines, bioinformatics, etc.
Linear time, that's a huge difference. Yeah, we've covered arrays, which are linear and generally fixed in size, and strings, which are sequences of characters. But what if your data isn't fixed? What if you need more flexibility to grow and shrink your list dynamically without all that costly shifting we talked about with arrays? That's where linked lists come in, offering flexible connections for dynamic data. How do they work? What's the core idea?
Right. Linked lists tackle that exact problem of inflexibility. A linked list is also a linear collection of data elements, but instead of being stored in adjacent memory locations like an array, these elements, called nodes, are scattered throughout memory and are arranged linearly with the help of pointers. Imagine a treasure hunt, or maybe a scavenger hunt. Each clue you find, that's a node, not only tells you something interesting, that's the data part of the node, but also gives you precise directions, like a map coordinate, that's the pointer part of the node, telling you exactly where to find the next clue in the sequence. So each node in a linked list typically contains two main parts, the actual data it holds, and a pointer, or link, that stores the memory address of the next node in the sequence. The last node's pointer usually points to a special value, NUL, indicating the end of the list.
Ah, I like the scavenger hunt analogy. Each clue literally points you to the next one, rather than having all the clues laid out neatly in a row at the start. That sounds incredibly flexible for adding and removing clues later.
Exactly. That structure gives linked lists their significant advantage over arrays, especially when it comes to modification. They allow for much easier, much more efficient insertion and deletion of elements, particularly in the middle of the list. If you want to add a new clue, a new node, between two existing clues, you just need to adjust two pointers. The previous clue's pointer now points to your new clue, and your new clue's pointer points to the clue that originally came after the previous one. No need to shift huge chunks of data like in an array. However, there's always a trade-off. The downside is generally slower access times compared to arrays. Because the nodes aren't necessarily stored together, you can't just jump directly to the 50th element using an index. You have to start at the beginning, the head of the list, and traverse the list sequentially, following the chain of pointers node by node until you reach the element you want. This is an ON operation for access compared to O1 for arrays. And just briefly, there are different flavors. Singly linked lists, pointers only go forward. Doubly linked lists, pointers go both forward and backward, allowing easier traversal in both directions. And circular linked lists, where the last node points back to the first node, creating a loop useful for things like round-robin scheduling.
Okay, so easier insert delete, but slower access. Makes sense. How do you go about traversing a linked list then, following that chain?
Traversing a linked list is done sequentially, exactly as the scavenger hunt analogy suggests. You use a temporary pointer variable, let's call it pointer, that acts as your current position marker. You start by setting pointer to the beginning of the list, which is usually held in a special variable like start. Then you enter a loop that continues as long as pointer is not a null, meaning you haven't reached the end, inside the loop. Step 3. Apply whatever process you need to the data part, info, of the current node pointed to by pointer. Step 4. Update pointer to move to the next node by setting it to the value of the link field within the current node. Set PTR a link pointer. You repeat steps 3 and 4, processing the node and moving to the next until pointer becomes a null. It's a straightforward step-by-step journey through the chain from beginning to end.
Got it. Process, then follow the link. And what about searching for a specific item within a linked list? Does its nature, whether the data is sorted or just randomly ordered, affect how efficient the search is?
It absolutely does. The time it takes to search a linked list heavily depends on whether the list is maintained in a sorted order or if it's just an unsorted collection. For an unsorted list, you really have no choice but to perform a linear search. You start at the start node, check if the data info pointer matches the item you're looking for. If not, you move to the next node, pointer, link pointer. You repeat this until you either find the item, then you set LOC pointer and exit, or you reach the end of the list, pointer becomes NL, in which case the item wasn't found. LOC equals NL. This is effectively the same as a linear search in an array, so its average and worst case efficiency is ON. Now, for a sorted list, say sorted in increasing order, you can potentially be smarter and stop earlier. You still start traversing from the beginning, but as you move along, you compare the item you're searching for with the data in the current node, info pointer. If the item is less than the current node's data because the list is sorted, you know immediately that the item cannot possibly be further down the list. It would have appeared earlier if it existed. So you can stop the search right there and conclude it's not present, set LOC equals NLL and exit. If the item equals the current node's data, great, you found it. Set LOC equals pointer and exit. If the item is greater than the current node's data, you continue to the next node, set pointer, link pointer. This optimization can make the average search time faster in practice for sorted lists, especially if the item is often found near the beginning or is determined not to be present relatively early. However, in the worst case, example, the item is the very last one, or it's not present but larger than all existing items, the search still takes ONE1 time because you might have to traverse the entire list.
Right, the sorting lets you bail out early sometimes. So, linked lists shine when it comes to insertion deletion compared to arrays. What are the typical ways you'd actually insert a new node into a linked list?
There are 3 main scenarios or ways to insert an element into a linked list, assuming you have available memory, often managed by an avail list of free nodes. First, inserting at the very beginning of a list. This is generally the simplest and most efficient insertion. Step 1, check if space is available. Avail.null. Step 2, get a new node, new from the avail list. Step 3, put your data into the new node. Step 4, make the new node's link point to the current start of the list. Step 5, update the list's start pointer to point to your new node, start inu. Step 6, exit. Just a few pointer reassignments very fast, O1 time. Second, inserting at a given node, or more accurately, after a given node location, LOC. Step 1, 3 are the same. Get a new node, put data in it. Step 4 is the key. If LOC is NNodel, meaning insert at beginning or list is empty, handle it like the first case. Else, LOC points to a valid node, set the new node's link to point to whatever LOC was pointing to. Link new, link locked, then update LOC's link to point to the new node. Link new. Step 5, exit. Again, primarily pointer adjustments, also O1 once you know the location LOC. Finding LOC might take ON though. And third, inserting into a sorted linked list. Here, the goal is to maintain the sorted order. You first need to traverse the list to find the correct logical position where the new item should go. You're looking for two adjacent nodes, say X and Y, where Y is link AX, such that the data in X is less than your item and the data in Y is greater than your item. Once you find this position, which takes O(n) time, you insert the new node between X and Y using the same pointer logic as inserting after a given node X, link new, link X, and link X is new.
Makes sense. Find the spot, then rewire the pointers. And what about the flip side? Deletion of a linked list node. How do you remove an element from one of these chains without breaking it?
The procedure for deletion from a linked list also centers around rerouting pointers to effectively bypass the node being deleted. Let's say you have node X pointing to node M, the one you want to delete, and node M is currently pointing to node Y. To delete M, you simply need to change the next pointer field of node X so that it now points directly to node Y. So link AX gets assigned the value of link AM. Node M is now effectively cut out of the active chain. Nothing points to it anymore from within the list. Often, the memory occupied by the deleted node M is then returned to that free pool of available nodes we mentioned, typically pointed to by the AVL pointer, making that memory reusable for future insertions. Like insertion, the pointer manipulation itself is O(1), but finding the node M and its predecessor X first might take O(n) time unless you already have pointers to them. But crucially, no data shifting is required, which is the big win over arrays.
Much cleaner than shifting potentially millions of elements in an array. Okay. And there's also something called a headers link list. What's special about that? Is it just a node at the front?
Yes, essentially. A header linked list is a variation that includes a special dedicated header node positioned at the very beginning of the list. This header node doesn't usually contain actual user data itself. Instead, it serves primarily as a consistent starting point, a fixed anchor for all list operations. This can actually simplify the logic for some operations, especially handling edge cases like inserting into or deleting from an empty list, or deleting the very first beta node. You always have this header node to work with, so you don't need special checks for an empty list as often. The header node can also sometimes store useful meta information about the list, like the total number of data nodes it contains. There are two common types based on how the end of the list connects. A grounded header list, where the link field of the last data node points to NUL, just like a standard linked list. And a circular header list, where the link field of the last data node points back to the header node itself, creating a continuous loop. This circular structure can be useful for certain algorithms that need to cycle through elements repeatedly, like managing a buffer.
Interesting. A dummy node to simplify the logic.
Okay.
Okay, now, sometimes you actually want to restrict the freedom of insertion and deletion. You want to enforce a very specific order or discipline, maybe to maintain linearity and regularity for certain tasks. That's where stacks and queues come in, offering controlled access for specific scenarios. Let's start with stacks. What's their fundamental principle?
Stacks are quite strict, yes. They operate based on a fundamental principle called LIFO, which stands for last in, first out. The classic analogy is a stack of plates in a cafeteria dispenser. You always put the new, clean plate right on top of the stack, and when someone needs a plate, they always take the one from the top. You can't easily grab one from the middle or the bottom. Similarly, in a stacked data structure, data can only be inserted, pushed, or deleted, popped, from one specific end, which is known as the top of the stack. It's literally a one-way in, same-way out kind of structure. This strict LIFO behavior is surprisingly crucial for many computing tasks, like managing function calls, undo mechanisms in software, or parsing expressions.
Last in, first out. Got it. So what are the basic actions you can perform on a stack given this restriction, and what are their common names?
There are really only two fundamental operations allowed on a stack enforcing that LIFO order. Push, this is the term used to insert an element onto the stack. When you push an item, you are adding it to the top. If the stack happens to be implemented with a fixed size array and it's already full, trying to push another item results in a condition called overflow. The algorithm is simple. Step 1, if top max size, print, overflow, and return. Step 2, increment the top pointer, set top, top plus 1. Step 3, store the item at the new top, set stack top item. Step 4, return, pop. This term is used for the removal of an element from the stack. When you pop, you are removing and usually returning the item that is currently at the very top. If you try to pop an item from a stack that is already empty, that results in a condition called underflow. The algorithm is similar. Step 1, if top item or -1 depending on convention. Print, underflow, and return, often a special error value. Step 2, get the item from the top. Set item, stack top. Step 3, decrement the top pointer. Set top, top 1. Step 4, return the item. These two operations, push and pop, are the only ways you're supposed to interact with a stack, ensuring that strict LIFO discipline is maintained.
Push and pop. Top, like FOFO. Very clear. Speaking of operations that might involve going back or repetition, that brings to mind the concept of recursion. How does that relate to stacks, and what makes recursion such a powerful, albeit sometimes tricky concept in programming?
Recursion. Yes, it's fundamentally the idea of repetition, or more accurately, a function or procedure calling itself back, either directly or indirectly. It's a powerful problem-solving technique where a function breaks down a complex problem into smaller, self-similar instances of the same problem. It keeps calling itself with these smaller instances until it reaches a simple base case that can be solved directly, without further recursion. For a procedure to be considered a well-defined, stable recursive procedure, it absolutely must have two crucial properties. First, there must be a base limit or criteria set. This is the condition, the simple case, that tells the procedure when to stop calling itself. It prevents an infinite loop of calls. Think of it as the exit strategy. Second, every time the procedure calls itself, it must be doing so in a way that moves it closer to reaching that base limit. Each recursive call should tackle a slightly simpler or smaller version of the original problem. If both these properties are met, the recursion will eventually terminate and produce a result. Now, where do stacks come in? This is critical. The computer system implicitly uses a call stack, often just called the stack, to manage recursive function calls behind the scenes. Each time a function calls itself, the system pushes a new frame onto the call stack. This frame contains information like the function's local variables and where to return to when this call finishes. When a recursive call completes, its frame is popped off the stack and execution resumes in the caller. The LIFO behavior of this call stack perfectly mirrors and enables the nested structure of recursion, keeping track of the chain of calls and where to return. A great example of where recursion shines is in divide and conquer algorithms like binary search or merge sort, which can often be expressed very elegantly using recursion.
So the stack is the hidden machinery that makes recursion feasible. Okay. Now, contrasting directly with stacks, we have queues. If stacks are LIFO, last in, first out, what's the rule for queues?
Queues are indeed the direct opposite of stacks in terms of access discipline. They follow a FIFO principle, which stands for first in, first out. Think of a line or a queue at a checkout counter in a store or people queuing up for a bus. The first person to get in the line is the first person to be served or get on the bus. In a queued data structure, insertion, often called unqueue, takes place at one end, which is known as the rear or tail of the queue. Deletion, often called dequeue, however, takes place at the other end, known as the front or head of the queue. So it truly has two distinct access points. One way in at the rear and another way out at the front. This FIFO behavior is fundamental to managing tasks that need to be processed in the order they arrive, like print jobs in a printer spool, handling network packets, or managing requests on a web server.
FIFO, like a real queue. Got it. And then there's a variation called priority queues. Do they strictly follow the same FIFO rule, or do they introduce, a priority twist?
Priority queues introduce exactly that, a priority twist. They are a more specialized type of queue where each element is assigned a priority value along with its data. When it comes to processing or removing elements, dequeuing, these specific rules are followed. Rule 1. An element with a higher priority must be processed before any element with a lower priority, regardless of when they arrived in the queue. So, if a critical task arrives, it jumps the line ahead of less important ones. Rule 2. And here's where FIFO comes back in. If two or more elements happen to have the same priority level, then they are processed according to their position in the queue based on arrival time. So FIFO applies as a tiebreaker for elements of equal priority.
Okay, so priority first, then FIFO for ties. How does insertion work then? Do you just add to the back and let the removal logic handle the priority?
Not usually for efficient implementations. For insertion into a priority queue, you typically need to place the new item in the correct position based on its priority right away. The general procedure is to conceptually traverse the existing queue, or underlying structure, until you find a node whose priority is lower than the priority of the item you want to insert. You then insert the new item in front of that lower priority node. If you traverse the entire queue and don't find any node with a lower priority, meaning your new item has the lowest priority among all existing items or the queue is empty, then it gets inserted as the very last element. A very common inefficient way to implement a priority queue is using a data structure called a heap, specifically often a min heap if lower numbers mean higher priority, or a max heap if higher numbers mean higher priority. A min heap, for example, is a specialized tree-based structure, often implemented using an array, that maintains the property that the parent node is always smaller than or equal to its child nodes. This guarantees that the smallest element, highest priority, is always at the root of the heap, making it incredibly fast to find the minimum. When you insert a new element, you add it to the end and then bubble it up heapify up by swapping it with its parent until the heap property is restored. This takes O log n time. When you extract the minimum, remove the highest priority item, you take the root element, replace it with the last element in the heap, and then bubble it down, heapify down, by swapping it with its smaller child until the heap property is restored. This also takes O log n time. While we won't walk through the C code line by line here, the core idea is using this heap structure to efficiently manage insertions and removals based on priority, ensuring logarithmic time complexity for these operations, which is much better than linear time searches in a simple list. This makes priority queues super useful for things like task scheduling in operating systems, event simulation, and graph algorithms like Dijkstra's shortest path.
Heaps. Okay, that sounds like a really clever way to keep the highest priority item readily available. Fascinating. All right, from these linear structures, we now move into a whole new dimension, you could say. Nonlinear structures. These tend to be more complex, often representing relationships or networks rather than simple sequences. Let's kick things off with trees and binary search trees, which seem to be all about hierarchical organization, maybe for faster access. What's the fundamental idea of a tree in data structures?
Right. Trees introduce hierarchy. A tree, in the context of data structures, is defined as a set or a collection of nodes, which represents some kind of hierarchical relationship between elements. If the set of nodes is empty, then it's logically called a null or empty tree. The defining characteristic is its hierarchical nature. Unlike linear structures, it's not just a sequence. It's centered around one special designated node called the root node. Think of it like the single ancestor at the top of an inverted family tree, or the main trunk of a real tree. From this root node, the data branches out. Typically in a binary tree, a node can have 0, 1, or 2 children nodes branching off it. If a node R has children, they're often referred to as forming a left successor subtree and a right successor subtree. This branching creates a clear parent-child relationship among the nodes flowing downwards from the root. It's a very natural way to model things like file systems on your computer, folders containing subfolders and files, organizational charts, or even the structure of an XML document.
Hierarchy, root, children, subtrees. Got it. And with that structure, there must be a whole set of new terminology to describe these different parts and properties, right?
Indeed. The hierarchical nature introduces some specific terms we use to talk about trees accurately. A few key ones include height or depth. This refers to the number of levels in the tree. More formally, it's the length, number of edges, of the longest path from the root node down to a leaf node, a node with no children. The height of the root node itself is considered equal to the height of the entire tree. A tree with just a root node has a height of 0. A full binary tree is a specific type where every node in the tree has exactly 0 children, it's a leaf, or exactly 2 children. There are no nodes that have only one child, it's perfectly branched or ends cleanly. And a complete binary tree is another specific type. It's a binary tree where all levels are completely filled with nodes except possibly for the very last level, the deepest one. And importantly, on that last level, all the nodes are filled in as far left as possible. This property is important because it allows complete binary trees to be stored very efficiently in an array, which is exactly how heaps, used for priority queues, are often implemented.
Okay, full versus complete. Good distinction. So, beyond just representing these relationships visually, what are the practical uses of binary trees? Why are they so important in the real world? Where do we encounter them?
Their practical applications are quite widespread and significant. They excel at representing relationships between data where hierarchy is involved. We mentioned file systems and org charts. They're also used in things like parsing expressions and compilers, decision trees in AI, or even representing the structure of game states in chess programs. They are superb at showing hierarchical data structures simply because their very nature is hierarchical. This makes complex, nested relationships much more intuitive to model and manage compared to trying to force them into a linear structure. And crucially, especially for certain types of trees, they provide very effective and often time-saving data searching. This is where specialized trees like binary search trees, which we'll get to, really shine. They can allow for incredibly fast lookups, insertions, and deletions, often much faster than linear structures for large data sets.
You mentioned searching and traversing. How do you go about traversing a binary tree? It's clearly not as simple as just going from left to right like in an array or linked list because of the branching. How do we systematically read or visit every node in a tree?
You're absolutely right. It's more nuanced. Because of the branching structure, there isn't just one obvious way to visit every node. There are actually 3 main standard recursive ways to systematically visit every node in a binary tree, plus a level-based approach. Each method visits the nodes in a distinctly different order, which is useful for different purposes. Let's use that family tree analogy. 1. Pre-order traversal. In this method, the rule is process the root node first, then recursively traverse the entire left subtree, and finally recursively traverse the entire right subtree. Think root, left, right. This is useful for tasks like copying a tree or creating a prefix expression. 2. In-order traversal. Here, the rule is recursively traverse the left subtree first, then process the root node itself, and then recursively traverse the right subtree. Think left, root, right. This method is particularly important and useful for binary search trees because, as we'll see, it processes the nodes in their sorted key order. 3. Post-order traversal. With post-order, the rule is recursively traverse the left subtree, then recursively traverse the right subtree, and finally process the root node last. Think left, right, root. This traversal is often used for tasks like deleting an entire tree, you delete children before the parent, or evaluating postfix expressions. And then there's also level order traversal. This isn't typically recursive. It processes nodes level by level, starting from the root. First, you visit the root, level 0. Then you visit all of its children, level 1 from left to right. Then all of its grandchildren, level 2 from left to right, and so on. This is like visiting everyone in one generation before moving down to the next generation. It usually uses a queue to keep track of nodes to visit at the next level. Each of these traversal methods is useful for different computational problems and gives you a different perspective on the tree's structure and content. For a specific example tray with root H, children E and D, etc., the traversals might yield sequences like pre-order, HEIGALBDKC, in order, IEAGBLHFCKDD, post order, IAABLGFCKDH, level order, HEDIGKALCB. Note, example orders, based on the provided outline, slight inconsistencies noted there might exist. Focus is on the pattern.
Wow. Okay, 4 different ways to walk through the same structure, giving different results. And building on that, you specifically mentioned binary search trees, BSTs, as being good for searching. What makes them so optimized for that particular purpose compared to a general binary tree?
Right. Binary search trees, or BSTs, are a specialized type of binary tree that are primarily designed and structured for one thing above all: incredibly efficient search, insertion, and deletion operations. They offer an average case running time for these operations that is logarithmic, O log n, which is very fast, especially compared to the linear time often required for unsorted linear structures like arrays or linked lists. Unlike a simple sorted linear array where insertion deletion is slow, or a basic linked list where search is slow, a BST provides a more advanced and often better balanced approach to managing dynamic data that needs to be searched frequently. The crucial requirement, the defining property of a BST, is that the data stored in each node must be comparable, like numbers or alphabetically ordered strings. And for every node in the tree, this rule must hold. All values stored in its entire left subtree must be less than the node's own value, and all values stored in its entire right subtree must be greater than the node's own value. This strict ordering property is what enables the efficient searching and maintenance, making BSTs an effective choice for various applications like implementing dictionaries, symbol tables and compilers, or sets and maps in programming language libraries.
The ordering property is key. So if you want to find something or insert something new into a BST, how do you navigate this ordered structure efficiently? How does that comparison work in practice?
The process for both searching and insertion in a binary search tree follows that ordering property very naturally and efficiently. You always start the process at the root node. You compare the value you're looking for, or trying to insert, with the data stored in the current node. If your value is less than the current node's data, because of the BST property, that if the value exists at all, it must be somewhere in the left subtree. So you discard the entire right subtree from consideration and recursively move down to the left child node. If your value is greater than the current node's data, you similarly know it must be in the right subtree if it exists. So you discard the left subtree and recursively move down to the right child node. You repeat these comparison steps, moving left or right down the tree, effectively having the remaining search space at each step, on average. This continues until one of two things happens. Either you find a node whose data equals your value, in which case for a search you found it successfully, or you try to move down to a child that doesn't exist. You hit an empty spot, a null reference, in which case the search was unsuccessful, the value isn't in the tree. For insertion, that null spot where the search failed is precisely where your new node containing the value should be attached, always replacing an empty reference area and maintaining the tree's ordering property. You wouldn't insert if the value already exists, typically. conceptually a C++ class might look like. Public class binary tree value extends, comparable value, private node value root, private class node value, private value data, private node value left right, public node value data, null designate. Other methods like insert, search dinull.
Searching sounds very much like binary search, but on a tree structure. Now, deletion, in pretty much any data structure we've discussed, often seems to be more complex than insertion. Is that true for binary search trees as well? It sounds like just removing a node could break that crucial ordering property.
Yes, you're absolutely right. Deletion in a binary search tree is indeed significantly more complex compared to insertion, precisely because you have to rigorously maintain the BST ordering property after the node is removed. You can't just pluck a node out and leave a hole or disrupt the order. Before you can delete a node, you first have to find it, using the search logic. Then you have to consider several scenarios based on how many children the node to be deleted has. Scenario 1, the node is a leaf. It has no children. This is the easiest case. You can simply remove it by setting its parent's corresponding child pointer, left or right, to null. Scenario 2. The node has only one child, either left or right. This is also relatively straightforward. You effectively bypass the node by making its parent point directly to its single child. Scenario 3. The node has two children. This is the most complex case. You can't just remove it, as that would leave two disconnected subtrees. The standard approach is to replace the data in the node to be deleted with the data from either its in-order successor, which is the smallest value in its right subtree, or its in-order predecessor, which is the largest value in its left subtree. Let's say you choose the successor. You find that successor node, which conveniently will have at most one child itself. Copy its data into the node you originally wanted to delete, and then recursively delete the successor node from its original position, which will now be an easier case 1 or case 2 deletion. This ensures the BST property is maintained throughout the tree. For example, if deleting root H and its successor is I, smallest and right subtree, you copy I's data into H's spot, then delete the original I node. It's about finding the most eligible contender to fill the gap while keeping the tree perfectly ordered and functional.
Okay, yeah, case 3 sounds intricate. Finding the successor or predecessor and then deleting that. Definitely more involved. So trees are great for hierarchies. But what if the connections are more free-flowing, more like a complex network of relationships? Maybe like social media connections where people can be connected in many ways, or a map of roads between cities. That sounds like it brings us to graphs in data structure. What exactly is a graph in this context?
Precisely. Graphs are the go-to structure when relationships aren't strictly hierarchical. A graph, formally, is a collection of points, which we usually call nodes or vertices, that are interrelated or connected by edges, sometimes called arcs or links. Think of that map analogy again. The cities are the nodes, vertices, and the roads connecting them are the edges, or a social network. People are nodes, and friendships or follow relationships are edges. These edges represent the connections or relationships between pairs of nodes. If the connection has a direction, like a one-way street or a follows relationship, the edge is often represented visually by an arrow. If it's a two-way connection, like a two-way street or a mutual friendship, it might just be a line segment connecting the two nodes. Graphs provide a very powerful and flexible way to model all sorts of real-world networks and relationships.
Nodes and edges. Makes sense. And you mentioned directionality. What's the formal difference between an undirected and directed graph?
The distinction lies entirely in the nature of the edges. When the edges in a graph have a specific direction associated with them, it's called a directed graph, or often shortened dgraph. If you have a directed edge represented as x, a, b, this means that the edge x originates from node A and terminates at node B. Think of it as a one-way street. You can travel from A to B along edge x, but not necessarily the other way around, using the same edge x. In this directed context, node A is called the origin or source of the edge, and sometimes the tail. Node B is called the destination or target, sometimes the head. We also say that A is a predecessor of B, and B is a successor of A. Both A and B are said to be adjacent nodes because they are connected by an edge. An undirected graph, conversely, has edges that don't have an inherent direction. If there's an edge between A and B, it implies a symmetric relationship. You can traverse from A to B and also from B to A along that edge. Think of a two-way street or a mutual friendship on Facebook. For example, a graph GVL, where V vertices is XYZ PQ and L edges links is XYX PYZ ZY PX PZ PQ would be a directed graph because the edges are represented as ordered pairs origin destination. Note the edge YZ and Z. Y indicate a two-way path is possible between Y and Z, but is represented using two directed edges.
Okay, directed versus undirected is clear. Now, with potentially many nodes and edges interconnected in complex ways, how do you go about traversing a graph systematically? How do you explore such a network without getting lost or visiting nodes multiple times unnecessarily?
That's a key challenge. With graphs, their nonlinear, potentially cyclic nature makes traversal more complex than trees or lists. To explore a graph systematically, we need algorithms that keep track of which nodes have been visited. Conceptually, during a traversal algorithm, each node can be thought of as being in one of three key states. 1, the ready state. This is the initial state for all nodes before the traversal begins. They are undiscovered and unvisited. 2, the waiting state. A node enters this state when it has been discovered, meaning we know it exists and is connected to a node we've already processed, but we haven't actually processed it or explored its neighbors yet. These nodes are typically held in a temporary data structure, like a queue or a stack, waiting their turn. 3, the processing state. A node enters this state when it's actively being visited. We process its data, and importantly, we look at all its adjacent neighbors. Once we're done with a node and have added its undiscovered neighbors to the waiting state, we often mark it as fully processed, sometimes a fourth process state, so don't accidentally process it again.
Ready? Waiting processing. Okay. And what are the main strategies or methodologies for performing this traversal, for deciding which node in the waiting state to process next?
There are two fundamental and widely used search methodologies for traversing a graph. They both explore the entire connected component of the graph starting from a source node, but they do so in fundamentally different patterns. Breadth first search, BFS, and depth first search, DFS. Breadth first search, BFS, explores the graph layer by layer. Imagine dropping a pebble in a pond, the ripples spread out uniformly. BFS works similarly. It starts at a source node, then visits all of its immediate neighbors, nodes 1 edge away. Then it visits all their unvisited neighbors, nodes 2 edges away, and so on. It covers elements breadthwise first, exploring nodes at the current depth or distance level completely before moving deeper into the graph. To achieve this level-by-level exploration, BFS typically uses a queue, FIFO, to manage the nodes in the waiting state. The conceptual algorithm looks like: Step 1, initialize all nodes to ready state. Step 2, put the starting node in a queue and change its status to waiting. Step 3, repeat steps 4 and 5 until the queue is empty. Step 4, remove the front node from the queue, process it, and change its status to processed. Step 5, for each neighbor of the just processed node. If the neighbor is in the ready state, change its status to waiting and add it to the rear of the queue. Step 6, exit. BFS is often used to find the shortest path between two nodes in an unweighted graph. In contrast, depth first search, DFS, explores the graph by going as deep as possible along a single path before backtracking. Imagine exploring a maze by always taking the first available path you see. You follow it until you hit a dead end or a node you've already visited. Only then do you backtrack to the previous junction and try the next available path from there. It covers elements depthwise first, diving as far as possible down one branch before exploring sister branches. To manage the backtracking and keep track of the path taken, DFS implicitly uses a stack, an EHOFO. This is often implemented recursively, where the function call stack acts as the stack. The conceptual algorithm provided in the source, Step 1, submit all nodes to ready state. Step 2, put first node in stack queue and change status to waiting state. Step 3, repeat 4 and 5 until stack queue is empty. Step 4, process the top first node, change status to processed, remove it. Step 5, add adjacent ready nodes of the processed node to stack queue, change status to waiting. Step 6, exit T, needs refinement to show the stack usage for DFS, but the core idea is pushing neighbors onto a stack and processing the top. DFS is useful for tasks like detecting cycles in a graph, topological sorting, or finding connected components. So while both BFS and DFS will eventually visit all reachable nodes, the order in which they visit them is fundamentally different, making them suitable for different kinds of problems.
BFS like ripples, DFS like exploring a maze path. That distinction is really clear. Okay, fantastic. Now let's explore some more advanced techniques that build upon these foundational linear and nonlinear structures. We're talking about things like advanced sort and search, hashing, self-balancing trees like AVL, and graph algorithms like Warshall's. To start, let's just circle back briefly to sort and search. We've touched on basic methods like bubble sort and binary search. What's the general overview when we talk about optimizing data retrieval at scale using more advanced techniques?
Right. Sorting and searching, as we've established, are truly fundamental operations. They're the bread and butter of making data useful. Sorting arranges elements into a defined order, which drastically enhances the efficiency of subsequent searching and often other processing tasks. Searching, of course, is about finding specific elements within potentially massive data sets. While the basic methods are great for understanding the concepts, when you're dealing with really large-scale data, think millions or billions of records, the performance differences between basic and advanced algorithms become astronomical. These advanced techniques are all about pushing the boundaries of efficiency, minimizing the time complexity, like getting closer to O(n) log n for sorting or O(1) for searching, and sometimes optimizing for space usage as well, making operations on massive data sets feasible in fractions of a second rather than hours or days.
Okay, and when we talk about sorting specifically, beyond just the algorithm's name, like merge sort versus bubble sort, what are the core complexities involved at a lower level? What are the actual machine-level actions that determine how efficient a sorting algorithm truly is?
That's a great point. Sorting involves more than just the abstract idea of arranging data like 1, 2, 3, 4n. At the machine or implementation level, the efficiency of a sorting algorithm boils down to the number and cost of a few fundamental operations it performs. Comparing of data. How many times does the algorithm need to compare two elements, A, B, or BA, to determine their relative order? Algorithms like merge sort try to minimize comparisons. Switching of the contents, swaps. How many times does the algorithm need to physically swap the positions of two elements in memory? Swapping can be relatively expensive, especially if the data elements themselves are large, like complex objects or long strings. Some algorithms, like selection sort, minimize swaps but might do more comparisons. Assigning of the data, moves copies. Operations like B of CB or CAA, which involve moving or copying data from one memory location to another, also contribute to the overhead. Algorithms like insertion sort involve many data shifts. The goal of designing efficient sorting algorithms is generally to minimize the total cost associated with these operations, often measured by the algorithm's time complexity, like O(n) log n for efficient comparison sorts, and sometimes its space complexity, how much extra memory it needs.
Comparisons, swaps, moves. Got it. And a very common operation, especially with sorted lists, is merging. We saw it conceptually with merge sort, what's involved there more formally.
Right. Merging is a fundamental operation, particularly key to merge sort, but also used elsewhere. Merging is defined as the process where two datasets, or lists, crucially both already sorted independently, are combined to produce a single, new, larger list that is also sorted. For example, if you have sorted list A with X elements and sorted list B with Y elements, merging them involves systematically comparing elements from the front of both A and B, picking the smaller one, adding it to the new list C, and advancing the pointer in the list from which the element was taken. You repeat this until one list is exhausted, then append the rest of the other list. The result is a new sorted list, C, containing all X plus Y elements. This merge operation itself can be done efficiently in linear time, OX plus Y. As mentioned, this is the core subroutine in merge sort, which recursively divides the list down to single elements, which are trivially sorted, and then repeatedly merges these sorted sublists back together. And just to briefly mention another advanced sorting methodology, there's radix sort. Unlike comparison sorts, like bubble, merge, quicksort, radix sort doesn't compare elements to each other directly. Instead, it sorts numbers, or strings, based on their individual digits or characters, starting from the least significant digit and moving to the most significant, or vice versa. It uses a stable sorting subroutine, like counting sort, for each digit position. For certain types of data, like integers within a known range, radix sort can actually be faster than O(n) log m, achieving linear time complexity O and WAC, whereon is the number of digits. It works somewhat like an old mechanical card sorter.
Merge sort and radix sort, different advanced approaches. Okay, we've covered basic searching in arrays and trees, linear binary, BST search. But what about highly specialized scenarios where you need absolutely lightning-fast lookups and potentially massive, unpredictable data sets? You mentioned hashing earlier as a key advanced searching technique. How does that work, and why is it often considered super fast?
Yes, hashing is a really powerful and widely used technique, specifically designed for scenarios where fast storage and retrieval are paramount. It often allows us to achieve near instantaneous lookups, insertions, and deletions, largely ignoring the total number of elements present. That's why it feels super fast. The core idea is this. Hashing takes any input data, it could be a number, a complex username string, maybe even the contents of a file, and uses a special mathematical function called a hash function to convert that input data into a seemingly random but fixed size numerical value. This value is called a hash code or simply a hash. This hash code isn't usually stored directly. Instead, it's typically used, often with a simple modulo operation, to calculate an index into a special data structure called a hash table. This index tells the system exactly where the original data should be stored within that table, which is often just an underlying array.
So the hash function tells you the address or slot in the table where the data belongs.
Exactly. It maps potentially huge or complex keys to a relatively small range of array indices. Hashing is used extensively in practice. Think databases, indexing records for quick retrieval, web server caches, storing frequently accessed pages, cryptography, generating checksums to verify data integrity, and implementing fundamental data structures like sets and dictionaries or maps in programming languages. Its major draw is its average time complexity for lookups, insertions, and deletions, which is typically O1 constant time. This means, on average, it takes roughly the same amount of time to find, add, or remove an item, whether the hash table contains 10 items or 10 billion items. This is achieved by directly calculating the storage location instead of searching through possibilities. The hash table, or hash map, is the data structure that brings this together. It uses an array as the primary storage and relies on the hash function to map keys to array indices, providing potentially superior performance for these operations compared to trees or lists, especially for high-performance applications.
Oh, and average time is amazing. Okay, so it's about rapidly figuring out where something should go, or where it already is, based on its key value via the hash function. What are the 3 key conceptual steps involved in the actual working of hashing? How does it handle the details?
Right, it boils down to 3 key steps or components working together. First, the hash function itself. This is the heart of the process. Its job is to take the input key and map it to an integer index within the bounds of the hash table array. A good hash function is crucial for performance and needs several properties. It should be fast to compute. You don't want the hashing itself to be a bottleneck. It must be deterministic. The same input key must always produce the same hash code and thus the same index. Ideally, it should uniformly distribute keys across all available indices in the table. This minimizes the chances of multiple keys mapping to the same spot. And relatedly, it should avoid clustering, where keys tend to map to adjacent or nearby indices, which can degrade performance in some collision handling schemes. Common examples of hash functions include the division method, hk by m, where you just take the key k modulo the table size m. Simple and often effective if m is chosen carefully, like a prime number not close to a power of 2. The multiplication method is another, using the fractional part of the product of the key and a constant. And there's the idea of universal hashing, which involves randomly selecting a hash function from a predefined family of functions at runtime to make it much harder for an adversary to intentionally cause many collisions.
Okay, a good hash function is vital. But what happens when, inevitably, 2 different keys do hash to the same index? That sounds like a problem. How's that handled?
That's the second key step, and arguably where much of the complexity lies. Handling collisions. A collision occurs when 2 different keys, when put through the same hash function, result in the exact same hash index. Since the number of possible keys is usually vastly larger than the number of table slots, collisions are practically unavoidable in any non-trivial hash table. When you try to insert a new key value pair and find its calculated index is already occupied by a different key, that's a collision. Techniques to resolve these collisions efficiently are absolutely crucial for maintaining good performance. There are 2 main families of techniques: A-chaining or separate chaining. This is perhaps the most common method. Instead of storing the item directly in the array slot, each slot in the hash table array acts as a pointer to the head of a secondary data structure, usually linked list. If multiple keys hash to the same index I, their corresponding key value pairs are simply stored as nodes in the linked list starting at hash tub li. To search, you hash the key to find the index, then do a linear search down the short linked list at that index. Chaining is generally good for handling dynamic data where the number of elements isn't known beforehand, and performance degrades gracefully as the table fills up as lists get longer. However, it requires extra memory for the pointers in the linked lists. B. Open addressing. This approach avoids using separate linked lists. If a collision occurs when trying to insert at index I, the algorithm searches for the next available empty slot directly within the hash table array itself, following a predetermined probing sequence. There are several ways to probe. Linear probing. This is the simplest. If index I is occupied, you just try I plus 1, then I plus 2, I plus 3, and so on, wrapping around the table if necessary until you find an empty slot. The drawback is that it tends to cause primary clustering, where long runs of occupied slots build up, significantly increasing average search times as the table gets full. Quadratic probing. To mitigate clustering, this uses a quadratic step. If I is occupied, you try I plus 1 bin array, then I plus 2 bin array, I plus 3 bin array, etc. Again, modulo table size. This helps spread out the probes more effectively than linear probing, reducing primary clustering, but can cause a milder form called secondary clustering. Double hashing. This is often considered the best open addressing method in terms of avoiding clustering. It uses a second independent hash function when a collision occurs. If the first hash gives index I and it's occupied, the second hash function calculates a step size s. The probe sequence then becomes I plus s, I plus 2s, I plus 3s, etc. Since the step size depends on the key via the second hash function, different keys that collide initially are likely to have different probe sequences, greatly reducing clustering.
Chaining with lists versus open addressing with probing. Okay. And the third step is just using these pieces for the actual operations.
Exactly. The third step involves putting the hash function and the collision resolution strategy together to perform the standard operations. For insertion, you calculate the hash index for the key using your chosen hash function. You go to that index in the table. If it's empty, or in chaining, if the list is empty or you're adding, you insert the key value pair. If a collision occurs, the slot is occupied by a different key, you invoke your chosen collision resolution technique, follow the chain, or start probing with linear, quadratic, or double hashing to find the appropriate place to store the new item. For searching, you calculate the hash index for the key you're looking for, you go to that index. You check if the key stored there matches your key. If yes, you found it. If no, either the slot is empty or it contains a different key, you again use your collision resolution technique to systematically check subsequent locations, the rest of the chain or the probe sequence, until you either find the key or you determine it's definitely not present. For example, you hit an empty slot in open addressing or reach the end of the chain. And for deletion, this can be slightly tricky, especially with open addressing. You first locate the key using the search procedure. Once found, you need to remove it. In chaining, you just remove the note from the linked list. In open addressing, you can't simply mark the slot as empty because that might break the probe sequence for other keys that collided there earlier. Often, you need to mark the slot with a special deleted marker, sometimes called a tombstone, so that searches can probe past it, but insertions can potentially reuse it. Managing deletion correctly to maintain integrity is important. Let's quickly visualize the chaining method with a simple C example. Imagine table size is 10. You have a hash function like key%table size. The hash table is an array of node pointers, initially all NLL. The insert key value function calculates the index, clues a hash function key. It creates a new node, sets its key and value, makes a new node next point to whatever hash table index currently points to, the start of the existing chain, possibly NULL, and then updates hash table index to point to the new node, effectively adding it to the front of the chain. The search key function calculates the index, gets the head of the chain temp f== hash table index, and then iterates through the while temp loop, checking if temp keys and following temp next until found or the end of the chain is reached. Display just iterates through the table indices and prints each chain. If you inserted 10, 100, 20, 200, 30, 300, and 25, 250, keys 10, 20, 30 would all hash to index 0, forming a chain. 30, 300, 20, 200, mine gone 10, 100, mino, LO. Key 25 would hash to index 5, forming 25, 250. Next in LO, searching for key 20 would hash to 0, traverse the chain, and find the value 200.
That C example really helps solidify the chaining concept. Calculate index. Manage the list at that index. Okay, so considering all this machinery, what are the overall advantages and disadvantages of using hashing in real-world applications? When is it great, and when might it bite you?
Right. Summarizing the pros and cons is useful. The advantages are compelling, which is why hashing is so popular. 1. Fast lookups, on average. As we stressed, the average time complexity for search, insertion, and deletion is 01, constant time. This is incredibly fast and makes hashing ideal for large datasets where you need quick random access based on a key, like retrieving user data by username or caching web objects by URL. 2. Efficient memory usage, potentially. Compared to structures like balanced trees, which might need extra pointers for balancing, or sorted arrays, which might need contiguous blocks, hash tables can often provide good memory usage, especially if the load factor, ratio of elements to slots, is managed well. Chaining uses extra memory for pointers, but open addressing uses the table space directly. 3. Relatively easy implementation. The basic concept of hashing and chaining, or even linear probing, is relatively straightforward to understand and implement compared to more complex structures like balanced trees. However, there are definitely disadvantages or potential pitfalls to be aware of. 1. Collisions are the Achilles heel. If your hash function is poor, or if you get unlucky with your data distribution, you can end up with many collisions. If the collision resolution strategy isn't efficient, or if clustering becomes severe, especially in open addressing, performance can degrade significantly. In the absolute worst case scenario, for example, all keys hash to the same index, the performance drops to ON, effectively becoming no better than a linked list. 2. Fixed size, often. Basic hash tables are often implemented with a fixed size underlying array. If the number of elements grows beyond the table's capacity or optimal load factor, performance suffers. While dynamic resizing, creating a larger table and rehashing all existing elements into it, is possible, it can be a complex and computationally expensive operation, causing a temporary pause in performance. 3. Poor performance for ordered operations. Hash tables are terrible for operations that rely on order, like finding the minimum or maximum key, or iterating through the keys in sorted order. These operations typically require scanning the entire table, making them ON, whereas balanced trees excel at these O log n or ON for full traversal. Hashing scrambles in natural order.
Great summary. Fast on average for lookups, but beware collisions and forget about inherent order. Very important points for anyone designing systems. Now let's look at another advanced tree structure we mentioned. AVL search trees. What makes them special compared to a standard BST, and why are they called self-balancing?
AVL trees are a really fascinating and historically important type of self-balancing binary search tree, BST. They were actually the first such structure invented, named after their Soviet inventors, Georgy Adelson-Velsky and Evgeny Landis, back in 1962. Their key feature, and the reason they're called self-balancing, is that they actively maintain a strict height balance to ensure efficient operations, even in the face of arbitrary insertions and deletions. Specifically, for every single node in an AVL tree, the height difference between its left subtree and its right subtree is guaranteed to be at most 1. This difference is called the balance factor, often calculated as height right subtree, height left subtree, and it can only be -1, 0, or +1 for every node in a valid AVL tree.
A maximum height difference of 1 between the two sides for every node. That sounds strict. So if you add or remove a node, and that balance factor accidentally becomes, say, +2 or -2 for some node, what happens? How does the tree fix itself?
That's exactly where the self-balancing mechanism kicks in automatically. If an insertion or deletion operation causes the balance factor of any node along the path back up to the root to violate that +-1 condition, becoming +2 or -2, the tree performs special rearrangement operations called rotations. These rotations are localized restructuring operations that involve rearranging nodes and updating parent-child pointers in the vicinity of the imbalance, effectively shifting subtrees around to restore the height balance property for all nodes, while crucially preserving the BST ordering property. This proactive balancing act ensures that the tree remains bushy or well-balanced, preventing it from degenerating into a long, skinny chain, which is the worst-case scenario for a standard BST. As a result, AVL trees guarantee a worst-case time complexity of O log n for search, insertion, and deletion operations. This guaranteed logarithmic performance, even in the worst case, is a huge advantage over a standard BST, which can degrade to O, worst case. That's why AVL trees, or similarly balanced structures, are highly valuable for implementing dynamic data sets in databases, memory indexing systems, and any application requiring consistently fast and balanced searching, insertion, and deletion, regardless of the sequence of operations.
Okay, guaranteed O log n through self-balancing rotations. That's the payoff. How are these trees typically represented? Is the balance factor stored?
Yes, when AVL trees are implemented, they usually use a linked representation similar to a standard BST, where each node contains the key, pointers to left and right children, and potentially a pointer to the parent. Crucially, each node also typically stores its current balance factor, the -1, 0, or +1 value. This balance factor needs to be updated efficiently during insertions and deletions to detect when and where rotations are needed. Sometimes, instead of the balance factor, the actual height of the subtree rooted at that node is stored, and the balance factor is computed from the children's heights when needed. Visualizations often show this balance factor as a number enclosed in brackets near the node.
And when you say rotations, what kind of rotations are involved specifically for insertion in an AVL search tree? How does it physically rebalance?
Right, the rotations are the core mechanism. When an insertion causes an imbalance, a node's balance factor becomes +2 or -2, the tree identifies the type of imbalance and performs one of 4 fundamental types of rotations or combinations thereof to fix it. These rotations are named based on the path taken by the insertion that caused the imbalance relative to the unbalanced node. 1. LL rotation, left-left. This is a single rotation performed when the imbalanced node becomes too right-heavy with balance factor +2, is caused by an insertion into the left subtree of the left child of the unbalanced node. It involves rotating the left child up to become the new root of the subtree. 2. RR rotation, right? This is the symmetrical single rotation. It handles imbalance. Node becomes too left-heavy with balance factor 9-2, caused by insertion into the right subtree of the right child. The right child is rotated up. 3 LR rotation left-right. This is a double rotation. It handles imbalance +2 caused by an insertion into the right subtree of the left child. It requires first performing an RR rotation on the left child, followed by an LL rotation on the original unbalanced node. 4 RL rotation, right-left. This is the symmetrical double rotation handling imbalance, 9/2, caused by insertion into the left subtree of the right child. It involves an LL rotation on the right child, followed by an RR rotation on the original node. These rotations seem complex, but they are precisely defined operations that involve rearranging a small, constant number of nodes, typically the unbalanced node, its child and grandchild along the imbalanced path, and updating their pointers to restore the balance factor property locally, which then percolates up the tree, ensuring the entire tree remains balanced with an O log n time for the insertion.
Single and double rotations based on the imbalance path. Okay. And what about deletion in an AVL search tree? Does it use similar rotation logic to maintain that strict balance after removing a node?
Yes, absolutely. Deletion in an AVL tree follows a similar overall procedure to deletion in a standard BST, handling the 0, 1, or 2 children cases, potentially involving finding a successor predecessor. However, the critical difference is that after the initial BST deletion step, removing the node or replacing it with its successor predecessor, the algorithm must trace the path back up from the point deletion towards the root, checking and updating the balance factors of all ancestors along that path. If any ancestor node's balance factor becomes unbalanced, +2 or 922 as a result of the deletion, because the subtree might have lost height, then one or more of those same rotations, LO, RR, LR, RL, must be applied at the unbalanced node to restore the AVL property. Unlike insertion, where usually at most one rotation, single or double, is needed, deletion can sometimes require multiple rotations propagating up the tree to fully restore balance. The logic determines which rotations to apply based on the balance factors of the unbalanced node and its taller child. For example, if a node becomes unbalanced with factor +2, B in some notations meaning height increased, a rotation might be executed. If the balance factor was already +1, B1, and deletion makes it +2, a different rotation might occur. If it was -1, B1, and becomes unbalanced, maybe an R1 type rotation takes place. The specific identities, like LOR0, LOR1, LRR1, correspond to different initial balance states leading to imbalance and require slightly different rotation outcomes to fix. It's an intricate but well-defined process to maintain that crucial O log n worst-case performance guarantee, even when elements are frequently removed from the tree.
Multiple rotations possible on deletion. Definitely complex, but ensures that guaranteed performance. Okay, shifting gears from balancing trees back to graphs, let's talk about finding all possible connections or paths within a network. That brings us to Warshall's algorithm. What is this algorithm primarily used for in the world of graphs?
Right. Warshall's algorithm, developed by Stephen Warshall back in 1962, is a classic and elegant graph algorithm. Its primary use is to compute the transitive closure of a directed graph. Essentially, it determines whether a path, direct or indirect, exists between any two vertices in the graph. It answers the question: for every possible pair of nodes, say I and j, can you eventually get from I to j by following one or more directed edges? It's important to distinguish it from algorithms that find the shortest path, like Dijkstra's or Floyd-Warshall. Warshall's algorithm isn't concerned with the length or cost of the path. It only cares about reachability. Is there a path? Yes or no?
Okay, so it's purely about connectivity.
Mm-hmm.
Can you get from A to B at all? Maybe through C and D, not necessarily the quickest way, just if it's possible. Like asking if two people are connected somehow in a complex social network, even through many intermediaries.
Exactly that. Can A reach B? That's the question. It answers for all pairs, A, B. It operates by systematically updating a matrix that represents the graph's connections. It uses a dynamic programming approach. It iteratively considers each vertex k in the graph and checks if using k as an intermediate stalk creates a new path between any other pair of vertices I and j. If you can get from I to k, A and D can get from k to j, then Warshall's algorithm concludes you can get from I to j, and it records this fact. The algorithm typically works on an adjacency matrix representation of the graph. This is usually a square matrix, let's call it G, where gauge is 1, or true. There's a direct edge from vertex I to vertex j, and 0, or false otherwise. Warshall's algorithm modifies this matrix in place to represent the transitive closure. It has the time complexity of O, or V, where V is the number of vertices in the graph. This cubic complexity comes from its 3 nested loops structure. Its main uses are, therefore, in finding all pairs' reachability, analyzing network connectivity, like determining if all components of a system can communicate, checking for cycles, and sometimes optimizing certain types of database queries related to relationships.
OBW. Got it. And what exactly is this concept of transitive closure that it helps to build? Can you elaborate slightly on that?
Sure. The transitive closure of a directed graph G is essentially another graph, let's call it G, which has the same set of vertices as G, but contains an edge from vertex I to vertex J in G if and only if there exists a path of length 1 or more, from N to J in the original graph G. In simpler terms, if you can get from I to J in G either directly or by hopping through 1 or more intermediate vertices, then there will be a direct edge from I to J in the transitive closure G. It captures all the indirect reachability information and makes it explicit as direct connections. Warshall's algorithm is a method for computing the adjacency matrix representation of this transitive closure graph G. It starts with the initial adjacency matrix of G, where Gj1 only indicates a direct edge. The algorithm then systematically modifies this matrix, adding ones based on indirect paths. The final matrix, produced by Warshall's algorithm, represents the adjacency matrix of G, showing all pairs ij for which a path exists.
Okay, it builds the matrix, showing all direct and indirect paths. How does the algorithm actually do that? What are the steps?
The algorithm itself is remarkably concise and elegant, based on that dynamic programming idea of considering intermediate vertices. Here are the steps. 1. Initialization. Start with the initial adjacency matrix graph VV of the given directed graph G. Graph EJ is 1 if there's a direct edge from I to J, and 0 otherwise. Often, graph E is also set to 1, assuming a node can reach itself. 2. Iteration over intermediate nodes. Iterate through all vertices K from 0 to V1. This K represents the potential intermediate vertex in a path. 3. Iteration over source nodes. Inside the K loop, iterate through all possible source vertices I from 0 to V1. 4. Iteration over destination nodes. Inside the I loop, iterate through all possible destination vertices J from 0 to V1. 5. Update reachability. This is the core step. Check if there's a path from I to J either directly, the current value graph uses 1, or R if there's a path from I going through the current intermediate node K, i.e. graphic is 1, A and D, graph KJ is 1. If either condition is true, it means J is reachable from I. Update graph E accordingly. This is often written concisely using Boolean logic, graph EJ, graph E Doj. This line says, the path from I to J exists if it already existed OR, if you can go from I to K and D from K to J6. Repeat. Continue these 3 nested loops until all combinations of K, I, and J have been considered. The final resulting graph matrix after all iterations represents the transitive closure. Graph EJ will be 1 if and only if there is a path, direct or indirect, from I to J in the original graph. Let's quickly trace the C example. Suppose V4 and the initial adjacency matrix is 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. The Warshall function runs 3 nested loops, K, I, J from 0 to 3. Let's consider when K1. It checks all pairs, I, J. For I0, J02, it calculates graph 0, 2, graph 0, 1, and graph 12. Initially, graph was 0, 1, and graph demo 1, and graph 12, 1. Graph 12 is 1, so 1 and 1 is 1, and 1 was 1, so graph 0, 2 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all K, the print matrix function shows the final transitive closure matrix. The Warshall function runs 3 nested loops, Kij, from 0 to 3. Let's consider when K1, it checks all pairs, Ij. For I0, J2, it calculates graph 0, 2, graph 0, 2, graph 0, 1, and graph 12. Initially, graph 0, point graph 0, 1 is 1, graph 12 is 1, so 1 and 1 is 1, foot 0, 1 is 1, so graph 02 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all K, the print matrix function shows the final transitive closure matrix, 1, 1, 1, 1. The Warshall function runs 3 nested loops, Kij from 0 to 3. Let's consider when K1, it checks all pairs. Ij, for I0, J2, it calculates graph 0, 2, graph 0, 1, graph 0, 1, and graph 12. Initially, graph 0, 2 is 0, graph 0, 1 is 1, graph 12 is 1, so 1 and 1 is 1, 0, 1 is 1, so graph 0, 2 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all K, the print matrix function shows the final transitive closure matrix, 0, 1, 1, 1. The Warshall function runs 3 nested loops, Kij from 0 to 3. Let's consider when K1, it checks all pairs, Ij. For I0, J2, it calculates graph 0, 2, graph 0, 2, graph 0, 1, and graph 12. Initially, graph 0, 2 is 0, graph 0, 1 is 1, graph 12 is 1, so 1 and 1 is 1, 0, 1 is 1, so graph 0, 2 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all K, the print matrix function shows the final transitive closure matrix, 0, 0, 1, 1. The Warshall function runs 3 nested loops, Kij from 0 to 3. Let's consider in K1, it checks all pairs, Ij. For I0, J2, it calculates graph 0, 2, graph 0, 2, graph 0, 1, and graph 12. Initially, graph 0, 2 is 0, 1, graph 0, 1 is 1, graph 12 is 1, so 1 and 1 is 1, 0, 1 is 1, so graph 0, 2 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all K, the print matrix function shows the final transitive closure matrix, 0, 0, 0, 1. The Warshall function runs 3 nested loops, Kij from 0 to 3. Let's consider when K1, it checks all pairs. For I0, J2, it calculates graph 0, 2, graph 0, 2, graph graph 0, 1, and graph 12. Initially, graph 0, 1, and 0, graph 0, 1 is 1, graph 12 is 1, so 1 and a 1 is 1, so 1 and 1 is 1, so graph 0, 2 becomes 1. This means we found a path from 0 to 2 via intermediate node 1. After the loop's complete for all k, the print matrix function shows the final transitive closure matrix. Now, graph 0, 2 is 1, reflecting the path found. Also, graph 0, 3 remains 1, direct path, graph 13 becomes 1, path 1 to 3, etc.
The triple loop systematically building up the connections. That C example makes the update logic graphic and graph KJ much clearer. Okay, so let's consider the practical side again. What are the main advantages and limitations of using Warshall's algorithm?
Sure. Warshall's algorithm has distinct pros and cons. On the advantages side, 1. Simplicity. It's conceptually simple and very easy to implement because its core logic is just those 3 straightforward nested loops operating on a Boolean matrix. 2. Works well for dense graphs. It's particularly well suited for dense graphs where a large fraction of possible edges actually exist when they are represented using an adjacency matrix. Its OV complexity is often acceptable in these cases, especially for moderately sized graphs. 3. Provides full transitive closure. It directly computes the complete all pairs reachability information in one go. However, it also has significant limitations. 1. Not suitable for sparse graphs. Its OV time complexity and OV space complexity for the matrix make it inefficient for sparse graphs with many vertices but relatively few edges. For sparse graphs, running multiple BFS or DFS traversals, which typically have complexity closer to OV plus E, where E is the number of edges, might be much faster and use less memory. 2. Can be unproductive for large graphs. The V factor means its runtime grows rapidly with the number of vertices. For very large graphs, say millions of nodes, over becomes computationally prohibitive. Other approaches might be necessary. 3. Does not provide shortest paths. This is a crucial point of potential confusion. Warshall's algorithm only determines reachability. Yes for no. It does not find the shortest path in terms of distance, weight, or number of edges. That task is handled by related but distinct algorithms like Dijkstra's algorithm for single-source shortest paths, or the Floyd-Warshall algorithm. Floyd-Warshall has a similar OV structure but works with edge weights to find the lengths of the shortest paths between all pairs of vertices. So remember, Warshall's for reachability, Floyd-Warshall for shortest paths.
Warshall for can I get there? Fulk, Floyd-Warshall for what's the shortest way? Excellent clarification. So, after this incredible journey, what does all this mean for you, our listener? We've traveled through the foundational principles of data structures and algorithms. We started with simple arrays and flexible linked lists, climbed through hierarchical trees and self-balancing AVL trees, navigated network-like graphs, and explored advanced techniques like hashing and Warshall's reachability. It's really clear, I think, that these aren't just abstract concepts buried in computer science textbooks. They are, in a very real sense, the unseen architects and the silent, tireless heroes working behind the scenes of our entire digital reality.
Precisely. Think about it. From the simple linear organization of an array that makes accessing elements by index lightning fast, enabling basic operations in countless applications, to the flexible connections of a linked list that allow things like your browser history or undo features to grow and shrink dynamically, from the intricate self-balancing act of an AVL tree that guarantees consistently fast searching, insertion, and deletion in massive databases that store your online profiles or financial records, to the network mapping power of graph algorithms like BFS, DFS, or Warshall's that help social networks suggest friends, GPS systems find routes, or systems understand complex dependencies. These techniques, these structures and algorithms are fundamentally what enable the incredibly fast, seamless, powerful, and frankly magical digital experiences we rely on, often take for granted, every single day. They are the essential tools that transform mountains of raw, meaningless data into usable, valuable, accessible information. They make sense of what would otherwise be utter digital chaos.
Digital chaos. Yeah, that sounds about right. Now, here's a provocative thought for you to maybe mull over after this deep dive. Imagine, just for a moment, a digital world without these underlying principles of efficient data organization and manipulation. What would that look like? How would your favorite apps even function? How would search engines possibly find anything relevant, anything at all, in the vast, sprawling ocean of the internet if they couldn't structure and search that data efficiently? What new unimagined challenges, what bottlenecks, what absolute limitations would arise as the sheer volume of data continues to grow exponentially day after day if we lack these fundamental tools, these clever structures and algorithms to make sense of it all? Perhaps the next time you search online, stream a video, or even just scroll through your photos, you'll have a newfound appreciation for those hidden structures and algorithms hard at play, silently, efficiently, making your digital life not just possible, but usable.